I'm Dorsa, I just started, and my research is really about designing algorithms for autonomous systems and robots that safely and reliably interact with people. So I'm interested in systems that look like this. So if you think about autonomy or robotics, as we see more and more of these systems, they're doing really well in factories, but we see more and more of them interacting with people in real world, working with people, collaborating with them. And then examples of these systems are things like autonomous or semi-autonomous driving, or robotic surgery, or service robotics, or maybe controlling drones from the ground. So I know these systems are very different from each other, but one major thing that they have in common is that they're all safety critical and they all need to interact with people. So although it's very difficult to come up with controllers for each one of them, and each one of them has a lot of difficulties and issues around them, there's this major thing that's the same, like across all these examples. They need to interact with people and they need to be safe. And if you think about autonomous systems or robots today, they're not necessarily very safe or interactive. And here I have some videos of some of these systems. So the first video is from the DARPA Robotics Challenge in 2015. So every roboticist shows this video. And it's kind of sad because there's a lot of work into each one of these systems. Like each one of these are very complicated, but they still fail. So this is from the competition in 2015. And as you can see, our robots today are not very robust or safe when it comes to dealing with uncertain environments or dealing with dynamic or uncertain environments. And it's not just robots. It's autonomous systems in general. So here we have a video of the Tesla autopilot crash where the car doesn't detect the truck on the side of the road, and there's a fatal crash. And also interaction is a big issue. We're not very good when interacting with other agents as robotics agents, especially if those agents are humans. So this is one of my favorite videos. In this case, the person has no idea what the quadrotor is doing next, and because of that, he doesn't know how to interact with the quadrotor or what to do next. So if you're planning for these autonomous systems, if you're writing controllers for these robots, we should kind of think about these scenarios. We should kind of think about the interaction between humans and the safety issues that are around that. And my research is about that. My research is about having autonomous systems, robots, interacting with people, and kind of the problems that are at the intersection of safety and interaction of some of these systems. And that's kind of between a bunch of different fields. So we really care about AI and learning and control. That's why I'm kind of both in computer science and electrical engineering, because we care about the math and we care about the AI and learning that goes behind some of these systems. But in addition to that, we care about human-robot interaction too. We want to build computational models of humans as these systems are interacting with people in real world. And if you want to talk about safety, we care about formal methods and formal techniques to be able to give any guarantees for the control or learning system that is underlying of some of these systems. So in my lab currently, we are thinking about various problems, and these problems kind of start from this idea of shared control or collaborative control when we have a robot and human trying to do a task together. And kind of on the same line, we are interested in building good models of humans, so we do a lot of intent inference, like let's say from vision, I want to predict what the person is going to do next. So we are interested in building these intent models of humans in collaboration. And sometimes it's competition too, but in shared control between human and robot. And also we are interested in building complex goals and complex models of humans. So if humans are, for example, expressive, we want to figure that out from the motion and maybe think of that when we are collaborating with a robot in kind of a human-robot setting. And this is for manipulation. This is also for navigation too. So we see this in social navigation when a robot tries to navigate around people. And there are also a lot of safety issues. So some of the problems you're currently interested in are things like safe learning. So if a robot is trying to learn and explore the environment and reduce the uncertainty about the environment or about the humans, how do we do that safely? Or what does safety even mean when you're using these learned components? So I'm not going to go over everything. I'm just going to go get deeper in one of the problems that we have started looking at and kind of what are the implications out of that going forward. And the specific problem is a problem of autonomous driving. So we did actually some work in driving. So imagine we have an autonomous car. And the autonomous car tries to optimize for reaching for its destination. So it's trying to go forward. And at the same time, it tries to avoid unsafe regions of the road, like the boundaries of the road. And if there happens to be another vehicle on the road, it treats that vehicle as a moving obstacle. So it basically tries to do collision avoidance with that car. But if you think about it, this vehicle is not just a moving obstacle that happens to sit there. There's a human inside it, And the human is also trying to plan for his own destination. And it's an intelligent agent. He's also thinking, and he's also deciding based on the actions of the robot. So if you think about it, whether we want it or not, or whether we plan for it or not, the actions of an autonomous car affects the actions of other drivers. And we do see this in our everyday lives. For example, when a car tries to change lanes, it starts nudging in and expects the other drivers to slow down and make room for it. So there are all these responses that are really happening. And what we wanted to do in this particular project was to kind of think about these responses, and even more than that, to leverage these responses for better safety, efficiency, and coordination. And the way we're modeling this interaction is as a dynamical system. So we are imagining that we have an autonomous car. Let's say that that's the orange car. And we have a human-driven car. That's the white car. And we have direct control over the actions of the autonomous car. So that's the steering angle and acceleration of the autonomous car. And in some senses, I can affect the person. I have indirect control over what the human can do. And let's call that UH. So that's the steering angle and acceleration of the human-driven car. So if you think about it, this is kind of like an underactuated system. So more specifically, what is really happening is that the autonomous car needs to optimize for its own goals, for its own reward function. And then we are modeling that as a reward function RR, where the autonomous car is optimizing that. And that's a function of state and actions, which is usual. But now I'm saying, well, this reward function should depend on the actions of the human, because we can affect the human. And well, one question to ask is, well, what does the human do? What is this UHS star? How do we come up with good models of humans? And the way we're modeling humans here is as agents who are approximately optimizing their own reward function, RH. So this picture alone has a lot of questions in it, like what is RH? How do I come up with a good RH? How do I make sure it works? How do I make sure it works in near accident scenarios? What should even be RR? Like what am I optimizing for the robot or for the autonomous car? And even if I have everything, how do I solve this? How do I actually solve this in real time on a vehicle that needs to interact with multiple vehicles? And if you think about it, this is a very difficult optimization to solve. This is a non-convex, non-linear optimization, nested optimization that I need to solve in real time on my vehicle to make this work. So lots of problems here. And I'm not going to go over all of them, but just to briefly talk about some of the issues that come up, let's talk about the reward function. So the way we are trying to learn models of humans is by kind of building this reward function that we are assuming humans are going to optimize. And specifically, the way we model that is by using ideas from learning from demonstration. So we gather trajectories of how humans drive, like in a car simulator. And from that, we are trying to build this reward function that we are thinking they're going to optimize. And specifically, we're using this approach called maximum entropy inverse reinforcement learning. And what that means is if I have an action that takes me to a better state, I'm going to weight that exponentially higher. So all I do is I gather trajectories. That gives me probability of UH. From that, I learned the reward function. We also assume some sort of structure for this reward function. So specifically, we're assuming it's a linear combination of a set of features, like things like collision avoidance or staying within your own road or your velocity or heading. And at the end of the day, based on the trajectories I collect, I'm learning W. I'm learning the weights. So I can do this offline, and I can build good models of humans. And that gives me a reward function of how humans are actually acting. And I can put that back in here and then try to solve my optimization. And to do the optimization, we are doing some math, and we are also doing some approximations to make this actually work. And I'm, again, not going into the details of that, but I just want to show you some of the implications of this. If I solve this on a vehicle, what will happen? So imagine I have an autonomous car again, the orange car, human-driven car. And imagine the autonomous car wants to change lanes. It wants to go to the left lane. So normally what autonomous cars do is they do something like this. They look at the velocity of the human, they project that, and they want to be safe. So they do something like this, slow down and wait for the human car to pass, and after that merge behind him. But what our car decides to do actually is actually something very different. It decides to cut in front of the person. And you might say, well, this is more aggressive. But the reason it does that is it has a model of the human. It knows if it cuts in front of the person is going to slow down and make room for it. Because it knows the person also doesn't want to collide, also cares about this collision avoidance thing. And I would actually argue this is more human-like. If I'm driving on Highway 101, I'm not going to wait for every single car to pass and after that change lanes, right? At some point, you start cutting in front of someone based on the model that you have, based on this model that, well, they're actually going to slow down. So if I do this, it'll be safe, it'll be OK. And this is actually safer and more efficient because that's kind of how we expect cars to drive on our roads. And that was kind of exciting because nothing was hand-coded here. This was just out of the nested optimization. And out of the nested optimization, the car decided to take this action without any hand-coding of if this, then that, or any sort of like hand-coding of the situation or the particular scenario. So this is kind of cool. And then we tried this for other scenarios, and I'm not going to go over it. But let me just go back to this picture. So I think we all agree to generate safe motion, we need to anticipate what this human might do next. And one way of anticipating that is by modeling this human as an agent who's approximately optimizing some reward function. And that was kind of the approach we started to think about. But then we saw this video. And here in this video, there's a truck driver, and there's a black car on the side of the road that's trying to change lanes. And it's doing everything right, signaling and everything right, until like now. And for some reason, this truck is not letting this car in. You might say, well, the truck driver is either asleep or drunk or really angry or completely out of it. And then the other driver was also kind of aggressive. Like if I was doing this, at some point I would give up. I would like, fine, this car is not letting me in, I'll go back to my lane. But the other driver kept pushing too. So if you think about our drivers on the road, we have different types of drivers, right? We might have different styles of driving. For instance, we might have aggressive drivers or timid drivers. We might have distracted drivers or attentive drivers. And when it comes to these interactions, between autonomous systems, you can't just rely on a single driver style and a single driving model with one reward function that models everyone, right? We need to actually differentiate between these driving styles of different people that are around us. So we're like, fine, OK, we can do this. So we took our formulation, we extended it, and we added a term. Let's call that term theta. And theta represents this driving style, how aggressive you are or how attentive you are. And now we can have a belief over this theta, and we can update that based on our observations. So I look at the white car. If I decide, based on my observations, I might decide this person is attentive or not attentive. And I can just update that as I go. But there is a problem with this. And that is, we got to get lucky to see any informative behaviors from the white car. For example, if I look at this turtle, it looks harmless. And I might go my whole life thinking that. But it's only when you start poking the turtle that you realize what sort of turtle you're dealing with. So right now, you're kind of stuck in the turtle situation. You're just observing the white car. We have no idea what type of driver the white car is. We're just observing that, and we're assuming what sort of driver it is. And there is no active information gathering happening. But if you think about it, the autonomous car, the orange car, is not just a passive observer that just sits there, right? It's also an actor. It can take actions. And we have already seen that its actions can affect the actions of other drivers. It can cut in front of people, and other people respond to that. So because drivers respond to the actions of other drivers, we have an opportunity here to actively gather information about their driving styles. So what that exactly means is I can take this formulation, I can change my reward function to now be a combination of reaching my goal, which is what it was before, and also another term that corresponds to information gathering, actively gathering information about the driving style of other drivers. So this information gain term is a difference between entropy over belief of my driving style at this time step versus next time step. So what is really happening here is I'm optimizing an expectation over this reward function, and that allows me to try to reach towards my goal, at the same time learn about the environment and explore the environment. And environment in this case is my belief of the driving style of the other agent, which was kind of cool. So thinking about the implications of that, again, if I have an autonomous car that tries to change lanes, in this case, what my autonomous car does is actually it starts nudging in. It doesn't just cut in front of people. It starts nudging in. And depending on how the other person responds, well, it might decide to go back to its lane if it decides the other driver is distracted. But if it decides the other driver is actually attentive, it completes the merge because now it has a better model of the person. It's updated this reward function in an online fashion. And again, all of this is out of optimization, no hand coding, which is kind of exciting. And we actually did a user study with this where we brought in users to drive on a car simulator. And what we saw was our humans, regardless of being attentive or distracted, they almost do the same thing when we are not using our algorithm. And by that, I mean we still have a belief of driving style. We're still updating that. But we are doing that update passively. We're not actively looking for anything. But if you're using our algorithm, there's a huge gap between how attentive drivers and distracted drivers drive, and kind of this gap is the thing that our algorithm creates and allows us to provide. And again, these are trajectories of real human data on simulators, so that's the average and standard error of how human drivers drove on a simulator. All right, so just to summarize this idea, so the key idea here was really that robots' actions affect the actions of humans or human drivers. So if that is the case, the thing we wanted to do was, can we leverage that for better safety, efficiency, coordination, and even estimation, as we see in the active information gathering case. So now I want to just briefly talk about some of the directions that we're currently thinking about based on some of the issues that came up during this project. So that's kind of the directions that the group is moving towards now. So going back to this interaction, the main thing that was learned here was a reward function. I was assuming that this RH is learned, and this is my model of the human. And if I've learned it exactly right, and if humans are following reward functions, then what's going to happen is that the autonomous car cuts in front of the person, and the person slows down. But the thing is, in reality, if you assume humans follow a reward function, they might actually follow a different thing. Let's call that R dagger H. So because I might not have enough data or might just not have the right features, it might happen that the human is following this other reward function, which is within some distance of the thing I've learned. But in that case, maybe the human car doesn't slow down as much as I liked him to slow down. And then if that is the case, there could be a collision. So this is a scenario that we are trying to analyze and we are trying to understand and kind of look at verification and safety issues when we have some of these learned components as part of our overall system. How bad could it be if I don't have a right model of the human? What sort of situations could arise? And this can actually help us in automatic test case generation when we're thinking about verification of some of these systems. So we have started thinking about some probabilistic guarantees for some of these systems. And also, this problem is not just about cars. It comes up in other applications. So another direction that we are looking at in terms of safety is having multi-agent safe learning. So we're looking at specifically the problem of having multiple quadrotors that are trying to interact with the world. Let's say we have two quadrotors that are trying to pick up an object, and we don't know the mass of the object. And there's decentralized control. So the problem specifically we are trying to address here is how can we safely learn about the environment? And the environment doesn't have to be the human. It could actually be something that's purely just about the environment, like the mass of the object. And we are thinking about safe set and exploration in these settings and minimizing the uncertainty while staying within the safety constraints. And also another direction, again, going back to the cars, is thinking about this interaction. Another big assumption that I was making here was humans are optimizers of rational reward functions. But if you think about it, when it comes to near-accident scenarios, humans are not optimizers or rational. They do the craziest things that we didn't even think about. So that's actually another direction that we are currently thinking about. How can we use ideas from bounded rationality to model humans in these near-accident scenarios? And we have started using the simulator at CARS, at Center for Automotive Research, to think about some of these experiments when we are looking at near-accident scenarios and how humans' attention and perception goes down and what sort of models should we look at when it comes to these near-accident situations. And thinking about more of a multi-agent setting of that, another direction we are looking at is shared roads, when we have autonomous cars and human-driven cars driving on a road together, and thinking about how these local interactions, autonomous car cutting in front of the human, how is that going to affect the longer goal of the network? Like, how is that going to affect traffic or throughput of the network? So we are kind of thinking about this interaction between local control and the network level properties that we care about. And more on the robot side of things, we're thinking about human-robot interaction in home settings. So we've recently bought a fetch robot where we are thinking about learning complex goals from humans by just observing humans and thinking about their intent or thinking about various expressiveness goals that we have. All right, so this is the group. And I can just take questions now.
Hi, given the recent rise of several autonomous vehicle accidents, I don't think our society is used to machines making decisions, and we have now figured out how to accept machines making faulty decisions. Mm-hmm. In the light of your research, you have assumptions of a human will adjust. And then there's different type of aggressive models or alternative models. However, if there was an incident, we hope not, but if there was one, is this a strong enough argument in front of court saying that we assume human user will respond to our...
That's a great question. So in the setup that we are looking at, actually, I didn't talk about the part that when we are modeling the human inside of the car. So there are two humans, really. One is the human-driven car. I have a fully autonomous car, and then there's a human-driven car, right? And one question is, how do I model that? There's also the human inside of the car, and we might actually want to model the human inside of the car, human's reaction time, if the human what needs to take over, what would happen. So far, we've actually looked at both problems there. And I strongly believe we need to use models and have models, representing models of humans, and these models could be machine learned, but they need to be expressive models, first off, and we need to understand how they're failing and where they're failing, and if they're failing, we need to be able to maybe transfer to a person or to kind of a supervisor that can figure out how to take over control, which is a very difficult problem, and we haven't solved that. And not having autonomous cars on the road, there are many reasons for that. One is we don't know if humans are going to accept this or not. We don't know who to blame. The sort of situations that comes up is very different from difficult situations are going to be very different from difficult situations when humans drive. So lots of issues there, but I think using learning is going to be part of it because of all the successes we've had, and at least in perception and building models of the environment or human. In some sense, we have to use learning, but there's a lot of work thinking about expressiveness or explainability of some of these systems that I didn't go over, but that's actually one of the directions that we are very excited to work towards.
Quick question on your assumption here around the environment. Do you consider the behavior to be different depending on the environment? So do you consider the context and all kinds of situations where, like you showed, it was on top of a house versus on the road? It's a complete different environment.
Yeah, that's true. Yeah, so there's known unknowns and unknown unknowns. So we are considering known unknowns, but not unknown unknowns. So we have a model of the environment. Like, for example, we hear about driving on a road or an intersection, or, for example, having a traffic light. So we do consider those and all the possible things that could happen in that environment. But if there's an earthquake and you haven't modeled that and that can affect something, we're not necessarily addressing that. There's one idea of using novelty detection in those situations. So if I'm far off the model that I have, can I detect that? And can I say something is wrong here? And again, another active area of research, being able to figure out that your model is actually incorrect and kind of backtrack and maybe do a safer thing if you're detecting novelty as part of your environment.
Hi, nice presentation, thank you. So the question is, does it also take into consideration the vehicle itself? Because think about the behavior of the human inside the vehicle is one thing, but if this is like a big truck, then it would take a lot of more time to stop than a normal car would be, right? So are you taking into consideration the vehicle and then maybe the environment other than that something?
Yeah, so to the extent that our simulators can handle that, we are considering that. So for example, if I'm driving on the car simulator, there's a specific traffic model of a Honda, and I'm using the dynamics of a Honda car. Or if I'm using a truck, that might have different dynamics, different tire forces. So we do consider that to some extent, but it's kind of limited to the simulations we're using. But in practice, that is something that should be considered, and I think with the methods we are developing, it would be easy to bring that in to have a different type of model driver. One thing that it doesn't consider is things failing over time, kind of degradation over time. So in that sense, I think we need to design more conservative algorithms thinking about degradation and those sort of problems. Yeah, right.
Do you also consider the behavior of the human being knowing that this is a self-driving car without a driver? Because I think also that may change.
Yeah, that's a great question. So we're looking at that in human-robot interaction, not necessarily in driving yet, but that's an active area of research, again, in HRI, thinking about adaptation and mutual adaptation. The fact that I know this is a robot now, my behavior is completely going to change. I do this personally. If I see a Google car driving on a road, I just cut in front of it just to see what happens, just to give it more information. So that is true that exists. And again, we're looking at adaptation in general in human-robot interaction, and there's a lot of nice theory around that. Yeah. Okay, all right.